Okay, thank you very much. My name is Melissa. In the previous tutorial, I have shown you how to design a steel connection using IDEA Statica and Robot Structural Analysis Professionals. Now, today, I will proceed the design of steel connections using IDEA Statica. Here, just I have this model that I have designed in the previous tutorial. Here this joint is designed before. Now today I will try to show you the design of these connections, and I will try to show you also uh, the singularity problems that will be happening while designing a steel connection using an idea Statica, and the local and the global buckling of the steel connection joints. Now here, just I will try to export these internal forces to the IDEA Statica using the add-ins link of the IDEA Statica. Now click this IDEA Statica so that all the internal forces will be exported to the IDEA Statica. Now it is taking more time. Okay, here this joint is exported. That is a connection to 87. Here this connection is exported. So here just you can see this is 287. That means the number of the name of the connection is connection 287. Okay, here just now you can select this one. While I select this, then the connection boundary box will be displayed here. So here just you can open these connections in IDEA Static. Okay, now all the internal forces are exported. Okay, good. This is the rafter, and this is the bearing support, which is the column. And here all those are the load combinations exported from Robots Structural Analysis Professional. Okay, for in order to make the analysis time be short, I need to delete the non-critical load combination here. This is, I think, the first one is the critical load combination with the maximum moment and the maximum shear here. But when we go to down here, the moment is becoming low, when the shear is becoming low, even the axial load is becoming low. But in this case, the axial load is greater than 110. Okay. So now let me delete all those loads. Okay, now I have to use these load combinations. So now here, this is, it is by default it is a bring member, but the rafters are not a bring members because this load will be transferred to the column, so the final bring member is column. So I have to set the column as bring member, so this support will come to this one. So now I will connect this member connected to this member. So all those options will come. I can use the welding, I can use the the bolt connection. So for the timing I will select this one, because as the movement is greater than 700, so I need to use brackets, as well as I have to use the stiffener. So click this one and now click OK. Oh, no, sorry, I'm not using this one. So this is it is a bank member, so I have to connect this to this one. So collect this one. Okay. So the board that I'm going to use is I need to use higher grade of boards, because the moment is it is too much. So in order to make boards pass and satisfy the requirements, I have to use higher grades and higher bigger size of boards here. Okay, here I'll just collect this one. So I need to use grade 10.9 bolts, and the diameter is it is M2. Okay, now click OK, and now click OK. So here, this is the connection. So now I will try to use the here I need to use the size of the plate, which is the 25. So the material is it is S355, and I have to use it is a bolted connection, not welded connections. So the arrangements of the bolts is to profile, and here at the top it is 10, at the left to 0, at the bottom I can use it is 550, and I need to increase the size of the plates, because I will be using more number of bolts. Then here I have to increase also the size of the hatch here. So the size of the hatches I can use the thickness is it is around 20. So the default is I can use S355, and related to the indie plate one. So this is the on member one. Sorry. So the depth is it is 515. Okay, this is the length is 550, and the depth is it is also 550. Okay. Here now let me reduce it to 500 little bit, because I need to use bolts at the in the edges of the plates. So now here the shape is triangular with flange, it's okay. Now the flange thickness of this is it is around I can use the flange thickness, it is 20, but here the web thickness is I can use it is 50. So the here it is the flange thickness, and the flange width is which is similar to okay, this the flange width must be similar to this one, so I have to use it is around 300. So now here this is the bracket, and I can move this the stiffener to this point, which is around 550. So here the X position is 500. I think it is 500. Okay. Here I think it is 550. Okay. just like this. So so now I will try to put the the bolts here. I have to move this to the I need to move this the stiffener to this point. So it is around 40. Its exposition is around 400. So I need to make the thickness it is 50. So it is both sides, and the exposition is nearly 200. I think it is 200, which will be coming to this one. So it is 180. Okay. So now I will try to just copy this plate to this one. Is 550, and now I did a copy of. Okay, no, sorry. So I can select this one, and the exposition is 550. It's now 550. So it is around 1000. Now let me select it. It is 1000. Okay, little bit it is lower. It is 900. Okay, perfect. So the location is at both sides, and here okay, sorry. So here I need to select the make the thickness of all the stiffeners. It is 50, and the location is at both sides. So now let me arrange. Let me provide the arrangement of the bolts. So to specify the arrangement of the bolt, I need to select the indie places. So here it is the bottom part. It is 550. This one it is 550, but I need to specify. Here it is 45. It is 45. Now let me make it a little bit higher. It is 65, because it has to have some distance from the the flanges of the beam. So the next bolts should be spaced, or should be located 70 millimeter from these bolts. So make it 70, and then here make it 70, and now here make it it is minus 70. So and then make it minus 70. So sorry. And now the next bolt will be located here. So okay, now then sorry. Now the next bolts will be placed 100 millimeter away from these bolts. So at at the bottom layer here, this one is it is 205. It is too much. So 65 is enough. And this one is also a little bit higher, so it is 50 is enough. So and also here suppose it is 70, and now it is 70, so it is 70, so it is 70, so provide is 70, so it is 70. Okay, now 1 2 3 4 5 6 7 8, 9, 10. Now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The 12 number of bolts that are required here. The right layer, it is 70. Okay, this one is also T70. So nearly the rows of bolts should be located. Okay, this one is it is minus 70. So okay, here bolts are arranged at the center of the end plate at both sides. So here now I will try to apply the welders here. Okay, welders are these are default. So now let me run the calculation here. Here the analysis is completed. Analysis it is 100% perfect, and the plate is 0.3, which is less than 5%, which is this is the plastic strain, the maximum strain of the plate. And here the bolts is the distance of the bolt says it is 96.5, which is less than 100. It is good. And when we come to also the weld, it is 98.1, which is a little bit, it is less than 100. It is good. So here our design is perfect. So here we can run the buckling analysis here. Just to go to the check. Go to the check. Here and now calculate the buckling analysis of the connection, because here it is buckling it is not calculated. This this gray color show that the utilization ratio is less than 60% for after, and for also stiffeners. But in the case of column, the utilization ratio is greater than it is 60. This shows the stress distributions of the columns and thereafter. Okay, here the analysis of buckling is completed. Okay, here the ratio is 8.39. So now let me check the buckling modes. Here this one is the critical one. So before that I have to show the buckling shape here. Okay, here there is a local buckling of flange here, and when in the case of the second mode with a factor of 9.69, here there is a buckling mode here is it is a local buckling here, and when we come to here there is also local buckling maybe around the brackets. Okay, here around here. The fourth one is the fourth buckling mode. It shows that there is a buckling around here, like this. So in the case of the first one here, 8.39, so we need to our this local buckling factor ratio has to be greater than 3, but in this case it is okay, because here there is a local buckling, not a global buckling. In the case of global buckling, all the members will fail in buckling, but in this case it is almost 97% of the members of the column is passing the buckling requirements. So there is it is a local buckling. So here just we can see the strain check here. So the strain is 0.3, which is this one. The maximum is 5%. It is okay. So the equivalent stress also. And here this is the equivalent stress distribution on members. Here this is the equivalent stress distribution on the members. The maximum is okay. Here this 355 it is around here. Okay, it is okay. So the bolt force. Here this is the bolt force. The maximum force will occur at the bolts, which is located at the tops of the plate here. These are around 82. This one is 84, and this one is 86. So the maximum, I think it is 80. It is around 88. Just like this. Okay. So here we can use also the stiffness analysis, which is we can shift it to the SCT mode. And then we can run the calculations here for the stiffness analysis. Okay, here the analysis is completed, and the design is also simultaneously completed for the stiffness design. So the design is at least the connection is okay. So it is the plate is 0.3, which is less than 5, which is similar to the strain the elastic plastic strain analysis. And here the bolts are okay, the welds are okay. Now I will shift to the capacity design here in order to analyze and design the connection for the capacity. So here just run the calculation of analysis and the design for the capacity check. Okay, now the analysis is and the design is completed. Okay, for the capacity design, the plate is it is less than 5. It is okay, the bolts are okay, the welds are okay, and the buckling is not calculated here. Now let me calculate the buckling. Okay, the analysis and the design of the joint for the case of the capacity design is completed. Okay, now let me check also the design joint resistance. Shift it to the design joint resistance option here. Then just click the calculate the analysis and the design of the joint for the design resistance checkup. Okay, here the design of the joint resistance checkup is complete here. All the requirement is okay. That is the plate is strain of all the plates of the beam, the columns, and the brackets, the stiffeners, all are okay. That is less than 5%. And the capacity of also the bolts is okay. It is 96.5%, which is less than 100. It is an economical design, and the world is it is 98.1%, which is less than 100. It is okay. So the design of the joint is okay. So here this concludes that the connection to 87, which is these connections, this connections is okay. These connections is okay. So this concludes the connection designs of an if using an idea STATICA. So thank you. Okay, thank you very much. See you next time.